Have you ever wondered how your favorite streaming service just knows what movies you'll like? Or how online stores can group millions of customers into these really specific categories? Well, it's not magic, it's all about finding hidden patterns in data. So today, let's dive into this incredibly powerful idea.
Okay, take a look at this. It's a chart showing customers' ages and how much they spend. Now, you and we can probably spot three distinct groups just by looking, right? But how in the world can a machine do this automatically, without anyone telling it what to look for? That's the big puzzle we're going to solve today.
And the answer to that puzzle has a name. It's a technique called cluster analysis, and its whole job is to automatically discover these natural groupings, or clusters, hiding in our data.
At its heart, the definition is actually beautiful and simple. We want to put things together that are alike, and we want to keep things separate that are different. Think of it like sorting a giant box of Legos. You're sorting them by color and shape, but you don't have the instruction manual for what you're building.
This whole process follows two golden rules. First, we want high interest similarity. That's just a fancy way of saying everything inside a single cluster should be very, very similar to each other. And second, we want low intersimilarity, which means the clusters themselves should be as different from each other as possible.
So what this really boils down to is a constant balancing act. A really good clustering algorithm is one that pulls all the members of a group in super tight, while at the same time pushing the different groups as far apart as it can. Usually it measures this with something called Euclidean distance, basically the straight line distance between 2 points. The goal is super clear. Minimize the distance inside each group and maximize the distance between them. And all of this falls under a really fascinating area of machine learning called unsupervised learning. The unsupervised part is key. It means we're not giving the machine any answers beforehand. We're not telling it what's right or wrong. We just give it the raw, unlabeled data and say, go find the structure.
Okay, so how do we actually do this? Let's get into our first major method. I want you to think of this one like building a really detailed family tree for your data. It's called hierarchical clustering, and it builds groups from the bottom up.
The process here is actually surprisingly simple. First, you just imagine that every single data point is its own tiny individual cluster. Then, the algorithm finds the 2 points that are closest to each other and merges them. And that's it. It just keeps repeating that process, finding the next closest pair and merging them over and over and over again. Let's actually watch it happen. So here we have 6 data points, A through F. The algorithm measures all the distances and, yep, it finds that A and B are the closest pair. So boom, they get merged. They are now our very first cluster. Okay, so now that A and B are one group, the algorithm looks around again. What's the next closest pair? Turns out it's D and E. So they get merged into their own little cluster. You can see how we're building up this structure one link at a time. And the process just keeps going. The next closest pairing is the new cluster we just made, D, E, and the single point F. So they all join forces, creating an even larger group. You can see how this hierarchy is just growing with every single step. And this is the final output. And it's brilliant. It's called a dendrogram, which is really just a fancy word for this tree-like diagram. But what it shows you is the entire history of all the merges. It's a complete visual map of how every single data point relates to every other one. It's not just a set of groups, it's a whole hierarchy of relationships.
Now, hierarchical clustering is fantastic, especially for visualizing those relationships, but it can be really slow on huge data sets. For that, we often turn to our second method, k-means. If the first method was a careful family tree, k-means is more like a quick, decisive sort into a fixed number of boxes.
And right there, that's the absolute key difference. With k-means, you, the person running it, have to decide upfront exactly how many clusters you're looking for. You have to specify that number, k. The algorithm itself is kind of like a dance in 4 steps. First, it just randomly drops k starting points, called centroids, onto the data. Second, every single data point gets assigned to whichever centroid it's closest to. Third, the centroids all move to the new center of all the points that were just assigned to them. And fourth, you just repeat steps 2 and 3 until the centroids finally settle down and stop moving.
So what is the centroid thing? It's nothing fancy, really. It's just the geometric center, or the average, of all the points inside a cluster. See the red crosses here? Those are the centroids. But there's a catch. A major weakness of K-means is that these centroids are super sensitive to outliers, which can really pull them way off course.
Which, of course, leads us to the million-dollar question for anyone using K-means. If you have to pick the number of clusters, K, right at the beginning, how on earth do you choose the right number?
Well, one of the most common ways is a technique called the elbow method. Basically, you run the algorithm with, say, 2 clusters, then 3, then 4, and so on. And each time you measure how tightly packed the clusters are. As you add more clusters, your score will almost always get better. But what you're looking for is the elbow. The point on the graph where adding yet another cluster doesn't really give you much of an improvement. That's probably your best K.
Okay, so we've covered the how, but what's the real payoff? Why does this matter? Let's talk about the real-world applications where this technique really, truly shines.
And the truth is, the applications are just everywhere. It's used to group news articles by topic, to help scientists discover genes that have similar functions, to create those customer segments we talked about at the beginning, and even to find stocks that tend to move together in the market. Its versatility is just incredible. So, whether we're analyzing massive amounts of climate data to find distinct weather patterns, or mapping out consumer behavior to understand shopping habits, the fundamental goal is always the same: find meaningful structure in what just looks like chaos. And the scale of that chaos can be, well, astronomical. For example, take a look at this number.
2 billion. I mean, that is just a massive number. What could it possibly represent in the world of clustering?
Well, that's the number of celestial objects. We're talking galaxies, stars, quasars, that were classified by something called the SkyCat project. Astronomers used clustering algorithms to automatically sort through radiation data from 2 billion different points of light in the night sky and find the natural cosmic groups. An absolutely stellar application, if you ask me.
So we've seen how machines can literally learn to find groups all on their own, from sorting shoppers to cataloging the entire cosmos. And that just leaves us with one final thought. What hidden patterns, sorted by algorithms just like these, are quietly shaping your world right now?